Okay, this experiment investigates absorption spectra of a set of linear molecules, which we're going to approximate as particle-in-a-box systems. Okay, so let's take a look at the theory for this experiment. Great. So the molecules we'll look at are these. Oops. They are di-D, which is diethylcyanine iodide, di-E, which is diethyl carbocyanine iodide, and di-F, diethyl dicarbocyanine iodide. Notice these molecules are identical except for the length of the carbon-hydrogen chain that links the two end groups. In the first case, it's 2 units long, 2 bond lengths long. In the second, it's 4 bond lengths long. And in the third, it's 6 bond lengths long. So we're going to approximate our system, these linear molecules, as boxes for electrons. And the only thing that will be different between them is the length of the box. So the first system here, second system, and third system are just one-dimensional boxes of different lengths. For the first system, the length is 2 alpha plus beta, where alpha refers to the carbon-carbon bond length. And beta refers to the extra length that's introduced by the end groups. Okay? Okay, we don't know what alpha and beta are, but we do know how the length had changed in terms of alpha and beta. All right. So as I mentioned, we're going to assume that the systems can be treated as one-dimensional boxes for electrons. And so the energy levels in each of these should be given by the standard formula for the energy levels of a one-dimensional box. H squared over 8 ml squared n squared. And if we see a transition between two states, then we expect the photon that's absorbed, that its energy will be equal to the energy of the final state minus the energy of the initial state. And so it should be h squared over 8 ml squared times n final squared minus n initial squared. Okay, finally, these boxes should be full of electrons. And the number of electrons depends on the molecule. The rule is 2 electrons per double bond in the chain, plus 1 per nitrogen atom in the end groups. And so following that rule, we get 2 plus 1 plus 1, or 4 electrons in di-D molecules in the first group, 6 electrons in the next one, and 8 electrons in the final one. Finally, when we go to interpret our results, we have to be a little bit careful. We expect these electrons will fill up the available states. And it has to fill up the states in accordance with the Fermi rule, which means that each orbital can accommodate 2 electrons, 1 spin up and 1 spin down. So for the first molecule, the 4 electrons fill the first 2 states. And that means that the lowest energy absorption transition that we can hope to observe would be the one from n equals 2 to n equals 3, because n equals 3 is the first unoccupied state. And we have to have an unoccupied state for the electron to move into. And as we go from die D to die E to die F, the number of electrons increases. And so the number of filled orbitals increases as well. And that will affect our prediction about what the energy should be. Okay? So with this background, you should be able to follow along in the lab handout and see how to analyze the data that you collect in the experiment. The goal of the experiment is, coming back here, is to find alpha, the length of the carbon-carbon bond. And you should be able to do that by fitting the absorption energy that you observe in each of the 3 molecules. Okay, good luck.